Okay, so what's your name and where are you from and where do you work?
Alright, hi kids. My name is Benoit, I'm from France. I'm from Montpellier in southern France, next to the border of the Mediterranean Sea, to the shore. And I'm a geologist, I'm a research scientist, and I'm here to work on rock samples to further understand the behavior of mid-ocean ridges and how the ocean crust is actually built at mid-ocean ridges. So, let's look at a few pictures together, alright? This is a map of the topography. It's a world map, it's a global map, okay? Here you have all the continents here, okay? You recognize South America here, Central America, the United States are somewhere here. This is the Atlantic Ocean, this is the Pacific Ocean. And here we just took the water of the ocean to actually look at the topography in the ocean as well. And in the ocean it's called bathymetry. The difference in depth, which corresponds to the difference in altitude when you are on land. Just to understand that when you are in the oceans, there are actually mountains and volcanoes and all kind of things that actually tell us about the dynamic of the Earth. And this is what we are trying to understand here. Okay, so we are now, if I can open this pen right here, we are now somewhere in the Indian Ocean. This is Madagascar here, and we are somewhere here. I will show that to you on a map later, okay? Now, let's step back a little bit and understand what does it mean in terms of plate tectonics and Earth dynamics. The Earth is actually made, the Earth's crust is actually made of plates. And each of the plates here is colored differently. You have, for instance, the Pacific plate in blue here, and the North American plate where you live is in dark blue, and you have the South American plate, which is in purple here. I live somewhere here on the Eurasian plate, okay? And the arrows here tells you which way these plates are moving one to each other. Sometimes they are converging, and if they do so, then this is the places where you create a mountain belt, like the Himalayas, for instance. And sometimes in other places they are diverging, they go apart, like here in the Pacific, and this is where we have mid-ocean ridges. The mid-ocean ridge where we are now is actually somewhere here. And you see you have one plate, the African plate, going north-west, and the Antarctic plate going southeast, and we are somewhere here where it opens. Okay? Now, another interesting thing is that these plates do not always move with the same speed, and therefore the opening along the mid-ocean ridges may have different velocities. Altogether, at the scale of the Earth, the velocities for this plate opening at mid-ocean ridges vary between something like 1 centimeter per year, and the fastest one is about 15 centimeter per year. And here, on the southwest Indian Ridge in the Indian Ocean, we are on a very slow one, which opens at about 1 centimeter per year. This kind of velocities, a few centimeters per year, it's about the same velocity as your fingernail growing, okay? Now, if you look at this other map here, it's a bit of a complicated map. I'll try to explain it to you. You have different colors. The colors are actually showing you the age of the oceanic crust, okay? And the red color corresponds to present day, zero age, or very recent, let's say 0 to 10 million years old. And then when you go to orange and yellow and green and blue and purple, it gets older, okay? So all of these colors in the ocean are from very young red to very old purple and dark and black here. Now, if you look at what's going on in the between, let's say, 0 and 30 million years old, which is somewhere in the orange color, if you look at this red to orange in the Pacific, it's much larger than it is here in the Indian Ocean. I will just put this because I'm shaking a bit, so it's going to be easier for Ali to show this to you. Here in the Pacific, this zone has the same age as this little zone here in the southwest Indian Ocean. So that actually shows you that this ridge is actually spreading much slower than this one. This one is faster, therefore the age of the crust, the 30 million years old crust, is further away from the ridge than it is here in the Indian Ocean. I hope it's clear, and if it's not, Ale will explain this to you later. Okay? So again, we are here, and now I will take my pen back. We are somewhere here on the Southwest Indian Ridge, and now I'm going to show you a map of where we are precisely. This white dot on the large map here is this map here, and you have the north. This is the north direction here, and the ridge is somewhere here. I'm drawing it with my pen. This is the Southwest Indian Ridge, and it goes here to the southwest. Okay, and it's offset here by this large fault, which is called a transform fault here. Here it's opening this direction, here it's going this direction. This is the ridge axis here. This is where it's opening. Here it's going this direction, it's going this direction. Okay, so here along this fault you actually have a movement like that. Okay, which is why it's called a transform zone. Okay, now where we are is here, this mountain here, this massif, which is a big massif. If you zoom in and you look at this map, this is the same place but now in a closer view. The top of the massif, which is here, is about 750 meters. The maximum depth somewhere in the transform fault here is about more than 2 kilometers, 2200 meters or even more, let's say 2500 meters. Okay, so you go from 700 to 2500, which is a lot. It's like a big mountain. Okay, and we are drilling somewhere on top of this mountain here, on this particular black spot here. Okay, and the reason why we are drilling here is that because on this very high massif, this topographic high here, we have rocks that have been actually created at the ridge axis here 15 million years ago, sorry, 15 million years ago, and they moved now to the present day position, which is this one.
Can you explain what happened to the top layers of crust here and why it was easier for us to drill here?
Okay, it's easier for us to drill here because on the top of this mountain here are exposed rocks that normally are found at the bottom of the ocean crust, somewhere at depths around 2, 3, 4, 5 kilometers. But here, specifically in this kind of dome massif here, they have been exposed by a fault. And a fault has actually bring these rocks up to the surface, closer to us, so that we can actually drill them from the seafloor to depths that we know where to drill to. Typically now we are at 700 meters, and we can access these normally deep rocks because they get closer to us.
Thanks, Benoit.
Okay, cheers.